good morning. So this is the last topic that we are going to cover. This is basically the topic of ensembling, ensemble of classifiers, and one interesting classifier that you would like to ensemble is the decision tree. So what's an ensemble? It's simply a collection of models. So each model might have been trained to perform the same task. For example, detecting spam email, you may have a classifier trained based on images, another classifier which is trained based on the source of the email, another classifier that has been trained based on the footer of the email. Now imagine combining all these classifiers in some intelligent way so that the consensus makes more sense. Okay, an ensemble can consist of many different versions of the same model or many different types of models. I mean, all of you do adapt ensembling. For example, machine learning. I am sure you would have visited 5 different university courses to understand the same concept, right? So maybe something is unclear here, you visit some other source, you get some clarity there. So it's a process that we adopt in our life. And why do we do that? Why do we create ensembling in our life? Why do we look at 5 different sources, let's say 5 different textbooks for understanding the same concept? Yes. All of them are meant for the same purpose. The way of explaining the concept can be different, yes. So you might register one way, someone else registers another way. So a one size doesn't fit all. That's the basic idea, right? So in plain words, what else? Any other way that you could think of justifying ensembling? So let's say there is noise that an individual model has brought in, right? There's possibly some noise. The noise could be in terms of overload of jargon. So same word can be used to mean a couple of different things, right? So for example, markov decision processes and reinforcement learning. Now 5 different textbooks will find different versions of what what cumulative reward is referred to as, right? So when you look at different sources, do you think that there is some kind of noise cancellation effect? The noise that you register by your reading or the rendering of that topic from one source, is it possible that the noise gets cancelled and you register the signal across these different sources? That's another motivation. Okay, so noise cancellation, and I'll mathematically characterize this intuitively though. Okay, so what you typically do is consider a weighted average or a voting of the predictions of different models in the ensemble. Okay, and democracy is largely about voting, right? So people express their opinion, and our hope is that any misgivings that one person has is not really transferable to another person, right? So kind of averaged over the people, we would expect that the right candidate gets selected. Okay, so voting, we all do that. Any of you stood for your general secretary position? Do you have experience campaigning? Anyone here? So nobody stood for any of the election process, election events here? So each of you has to, I mean the person who's the candidate has to basically champion the cause, right? And maybe the people don't register the cause the same way that you wanted to communicate, right? But then the hope is that on an average somebody gets your idea, not somebody, a majority of the people get your idea. So this is everywhere, this is commonplace, and therefore the belief also that the ensemble of different models that all achieve similar generalization performance often outperforms any of the individual models. Instead of one person deciding, let the mass decide. So question is, how can we make this possible? Okay, so let me just register some of the keywords. So through ensembling we want noise cancellation, better customization, better generalization, better generalization of customized models, right? So across customized models. Customization is where we talked about one size fits all. So and then the intuitive voting, / weighted averaging. So voting is where everyone is given equal importance, but in weighted averaging you may give different importance to different people, different classifiers, different models. Okay, so just to impress upon you the importance of this entire paradigm. So 2009, this is pretty old, but then this is when deep learning wasn't around. People were not able to throw large amounts of data and get models to learn. So even in that time, in that situation, ensembling was very helpful. In fact, the top of the leaderboard, the first two were actually ensemble models. The winning team used an ensemble of 450 plus different models. This winning team. This is Belcour's pragmatic chaos. Okay, so even the second one, the name itself is the ensemble. So it works in practice. Okay, then here's the intuition. Let's say I have multiple binary classification functions. Let's start with simple classifiers, binary classifiers. And let's say on an average they have the same expected error rate. Okay, so less than 0.5. So error is less than 0.5, which means each classifier is slightly at least better than a random guess. Okay. By random guess I can get 0.5 error rate, but we are expecting that the error is less than 0.5, so it's better than a random guess. And we say expectation over the distribution of the data. It's an unknown distribution, but that's the assumption we make. Okay, so now under this assumption what could you do? So now we have given some more context under which you can do this weighted averaging. So under this, it's the what will turn out is that the majority of the K classifiers in the ensemble will be correct on many examples. So an individual classifier might make an error, but a majority will be correct. Okay, and one way to pictorially understand this, okay, they're all classified the same, targeting the same problem. So the idea is that this region where the one specific classifier disagrees from the other classifier, right, is the region where most of the others will disagree. The place where they'll agree, most of them will agree, will far outweigh the regions where one of them disagrees from the other. Okay, that's the basic intuition. Majority of the K classifiers in Ensemble will be correct on many examples because they were all trained to cater to the same problem. Okay, so a simple majority vote can significantly improve classification performance by decreasing the variance. Okay, so now we get into bias variance. So across these classifiers we will be able to reduce variance, that's the idea. Okay, so let me give you some mathematical expression. So let's say the variance in prediction of a single classifier, let's say, was sigma square. And now I consider a weighted average, an average just to begin, let's say simple average. So what will be the variance of average of n classifiers? Okay, and let's say that the correlation, we've done correlation coefficient, statistical correlation coefficient. Let's say the average correlation between any two classifiers is rho. Okay, so you could show above. So you could show that if the average correlation is rho, just let's say instead of average, just the correlation is rho. Okay. Correlation between two classifiers is rho, correlation of prediction. Sigma square is the variance, and the variance of the average, you can show it will be rho times sigma square plus 1 minus rho times sigma square by n. So if the classifiers are independent, right? The classifiers are independently chosen, and if there are a large number of classifiers, n is very large, then what do you expect? The rho sigma square, the first term will dominate, and even there, if the rho is very small, basically the variance is shrinking. This is a basic idea. Okay, so basic idea is reduce rho, increase n. Okay, have these classifiers independent of each other. You really want independent opinions. I mean, that's what you would like even in election, in democracy. You would like people to think independently. But at the same time, you want a large number of people to vote. Okay, so this is the base, I mean, intuition. The same intuition has some mathematical justification. So question is, how can we come up with such an ensemble? Yeah. How I got, we can discuss it offline. I mean, all we are saying is these are the same correlation coefficient for all pairs. So that we are making some assumptions here, right? And they all have the same variance. Under this assumption, it's not very difficult to show this expression. So basically looking at how much they are correlated times sigma square and how much they are not correlated divided by the number of examples that you are considering. Yeah. Right. So the attempt is, we'll look at methods. The attempt is to make them really independent. So that's the starting point here. This is what we ideally prefer. The ideal preference is that the errors they make are independent. Okay, this is ideal. But how can we come up with such an ensemble? Can we even come up? Well, there are some approximations.
Here already this expression is less than improve the.
So the just one justification is this expression is already less than sigma square. We are trying to make it really small. In some sense independent of what the original sigma square were, because we are trying to shrink it to 0. But even if not, there is some reduction. Okay, so how do we come up with such an ensemble? As I said, we start with the ideal, but then we look at what's practical. So independence is what we are targeting, but simple ideas like dropout in deep neural networks. Dropout basically is hinged on idea of ensembling. It lands up performing regularization, and we all know that regularization was meant to help generalize. So one of the objects was better generalization. We discussed regularization at length. So also bagging and boosting, which we will discuss today and then continue with decision trees. So I mean, I don't want to do a one-to-one association, but yes, bagging is directly motivated by noise cancellation. Dropout, is directly motivated by generalization, but it does help achieve some of the other goals. And boosting is kind of more directly, intuitively motivated by an average, a weighted average. Okay, and there's this interesting effect of balancing bias and variance that we talk about in bagging and boosting. Let's quickly discuss what dropout does in deep neural networks. As a first example, I've referred to the section of the book, Yoshua Bengio's book. So what dropout does is says, well, I'm going to mask away certain activation units. I've just shown a small snapshot. The connections we are shown from the L-1th layer to the Lth layer in a deep network, and what you do is using a random variable, a mask variable mu, you can which is binary, and you have these mask variables sampled independently from each other. Okay, same idea, this independence that we want, we want to kind of reduce correlation, So to ensure to do that, sample the mu's independent of each other, and there is a hyperparameter by which you decide with what probability the mask should be 1. So probability that mu is 1 equals beta is a hyperparameter. For example, beta equals 0.5 is often chosen for the hidden layers and beta equals 0.8 for the input. But that's really a choice driven by engineering. So each of these resultant the mu i's, that is sigma i's multiplied by mu i's, is multiplied by 1 upon beta to basically ensure that we have probabilistic semantics maintained. Why? Because we are going to now multiply these by the weights, and later on we are going to consider multiple such instantiations of the mu's, right? Because we are talking about mu's as coming from a probability, underlying probability distribution. So you just pre-multiply this by beta along with the mask. Now it turns out that this simple process is an ensembling process. And how is it an ensembling process? Can someone suggest? What's exactly happening here? So each run is now corresponding to a different neural network. So what are we doing in this process? We are saying that so one of these networks has only the sigma 1 and sigma 3 in the L minus 1th layer, and sigma 2 in the Lth layer. There is another network which has sigma 1 and sigma 2 in the L minus 1th layer, and sigma 3 is masked out. Okay, so this corresponds to a choice of mu 2 sigma L minus 1 is 0, mu 3 L minus 1 is 1, mu 1 L minus 1 is 1, mu 2 L equals 1. Whereas in the second case, mu 1 L minus 1 was sampled to be 1, mu 2 L minus 1 was sampled to be 1, and mu 3 L minus 1 was sampled to be 0. Like before, mu 2 L was sampled to be 1. Okay, so now each such sampling corresponds to an instantiation of a part of the network, and you are basically considering an average. Equal to randomly selecting one of the subnetworks and running forward propagation through it and then averaging. So final network is a combination of exponentially large number of similar neural networks. So in some sense what dropout training corresponds to is looking at some expected error rather than the error resulting from one instantiation alone, where the expectation is now with respect to the distribution on mu.
All these subnetworks are different from the original idea of ensemble in that the parameters are kind of shared, right? Because you're not independently training the exponential number of networks, you're sharing parameters across.
Here we are.
Yes.
Yeah. So his point is in this process the network parameters are all shared, because you will kind of sample again from the mu, start from the previous values of the weights, do a back propagation and get your new estimates. So you are not starting the parameter estimation from scratch every time you sample the mu's. Is that point clear? I will show you in the next slide. So what's happening is you have the same base network. You have a base network. The parameters for the base network form the starting point for any of these different instantiations. Okay, the parameters for subnetworks are initialized with params, okay, weights from the base network from a previous epoch, previous iteration. So their weights are basically shared or not completely independent. So as I said, each of these will become an approximation to what we are targeting, right? So they are not completely uncorrelated, but yet in the process we would expect reduction in variance. To the degree to which they are correlated, to that degree we will not have the desired reduction. But there is an attempt to get some reduction. Somebody had a question? We can't exactly use this because the variance of a single classifier which we assume was sigma square, I mean that itself is subject to change with the model itself has changed. Right. So this is just a motivation. That's why I am not going into great details with this idealistic assumption, right? Each of them should have the same sigma square and so on. But this is a motivation. So question is, how is this implemented? This is what it turns out to be. The implementation, you can just do back propagation with dropouts, a simple change, and the only change here is as follows. So you will sample new p's, you will sample them. The forward propagation we already discussed that once you decide to mask out a sigma, you will not count it, but when you mask in a sigma, you will multiply it by 1 by beta, okay, because the beta is the probability with which a mu would have been 1, and thereafter again after getting the output, you would have multiplied by the mu at the target activation unit. In back propagation, what are you doing? We are just keeping track of what mu's contributed, that's all. Back propagation is basically based on bookkeeping. Okay, that's it. So here the bookkeeping is that if mu I mu j L was 1, then let the back propagation account for the gradient that you are getting from the next layer. This is a gradient you would have obtained from this next layer from sigma PL plus 1 from some sigma P sitting here, right? So you just mind the contribution based on mu, that's it. Okay, this is a simple idea of dropout as an ensemble method. The second idea which will lead to bagging is that, well, if you want the classifiers to be not correlated, instead of masking away certain substructure in a complex architecture, pick some other black box simple architecture, but train that architecture on different data sets, change the data set, that's the idea here. Okay, so the first idea was dropout, the second is make data sets independent. Okay, so you have D1, D2, D3 and Dn, n independent data sets. So I call it T. Let me be consistent with that. TR1, TR2 and TRn, and based on each of these you learn this independent model F1x, okay. Now because these data sets are independent, I would again expect that the correlation rho between the models learned from these independent data sets would be low, right? Ideally, they are not correlated at all. So classifiers trained in this way are guaranteed to make independent errors on test data, because the data sets, if they are ideally independent, then they are guaranteed to be not correlated. So if the expected error of such a classifier is less than 0.5, then the weighted majority is guaranteed to reduce the expected generalization error. So error of course should be less than 0.5. The 0.5 thing. Yeah, 0.5, as I said in the beginning itself, 0.5 makes sense only for two classes. If it's n classes, it will be if the k classes, 1 by k. Okay. So if the expected error of each classifier is less than 1 by k in the case of k class classifier, then the majority vote is guaranteed to reduce the expected generalization error. Look at majority. You could also look at weighted majority if you had probabilistic estimates. Okay, so if you had probabilistic estimates, so you will say the probability of a class Ck given x would be an average over the probabilistic estimates from these classifiers I equals 1 to n of fi Ck given x. And now you can do a convex combination of these to maintain the probabilistic semantics. You can say this is alpha I times alpha I, for example, could be just 1 by n. So if you had if these FIs were not if FIs could give you probability values, then you could also consider these weighted average. Now what is the weakness of this approach? What is impractical about this approach? Could you implement this? Small training sets. So if you really want these data, the training sets to be independent of each other, you will basically have to create only small chunks of a large data set. The training sets might turn out to be very small. So we may have to compromise on the size of each data set. And when we say compromise, we mean that very small. And what happens if the data set size is too small? The classifier will turn out to have high variance. Okay. So a compromise, I mean a middle path will be, well, I'm not going to make the data set size too small, but I'm going to sample these data sets from the same old data set with replacement. So I'm going to sample with replacement, and that is bagging. Okay, that's the second approach. What bagging says is I can't effectively achieve independent data sets, so I'll do this bootstrap aggregation where I'll do bootstrap sampling on the same data set. So these are not independent, and what I'm going to do, instead of independent data sets, I'll say these are large data sets, and because I don't want to make them too small, I'll say I'll also sample with replacement. So I might land up sampling the same instance multiple times. So you'll sample as many times as the number of classifiers you want to learn. Okay, so of course the trade-off we have now is that the errors won't be totally independent because the data sets aren't independent. But the process of resampling gives you enough diversity. So basically what will happen is the coverage of the data set will be, you will kind of ensure that it's large, and because you are sampling with replacement, you are trying to maintain some independence, though obviously you are not guaranteed independence at all. Okay, you are trying to reduce this correlation coefficient. So it may still happen that the individual classifier has high variance, but at least what you would like is that individual classifier has low bias. I mean, there is no point in having a single classifier based on a sample of the data set, which will mean that its variance is not going to be the same as whole variance. Variance is increased, but if the variance is increased, at least I want the bias to be low, right? So typically bagging is performed on models which have low bias, so that through the process where the variance increases on each fold, when I do an averaging, the variance can also reduce. That's why I said in the beginning that this bagging basically balances bias and variance. But let me write this in words. Okay, so the idea is that bootstrapping might increase variance, aggregation will again try and decrease the variance. Okay, so bootstrap might increase variance, aggregation again decreases variance. And in the middle of that, all this, we would like that the base model has low bias. So decision tree is often chosen here, and that this is also the motivation. I mean, we will continue with decision tree, hopefully get started on it today. So this is an example. Bagging is historically closely associated with decision tree model, which we will cover in the class. And when I say high capacity models, I also indirectly am hinting at low bias. The bias is low, it has high capacity to learn a wide range of classification models, and that's why decision trees are good. Of course, your lab associates bagging with perceptron as a weak learner, so we can get started with the lab today even as we discuss decision tree. And a random forest classifier is a popular extension of bagging for decision trees, but we will come to random forest when we discuss decision trees. You can also do bagging on deep neural networks. So for example, all you will do is uniformly at random with replacement sample subsets of the training data. You also can sample subset of the features of for example the input layer features. Okay. So you are doing two things here, subsetting the data and also subsetting the input layer features, and the deep model NS is resulting from both of these. Okay, and what is the bagging algorithm? So whatever we may specify here, you have a simplified version of this that you will implement in the lab. because in lab you will deal with perceptrons, and here we are dealing with a multi-layered network, right. So the bagging algorithm is draw this bootstrap sample of size ns from the training data, and also you could also sample a small feature set, sample phi s from the entire feature input features, learn the model, and the ensemble will be will be based on averaging. So here is the pictorial depiction. So you will have let us say I use some sigmoid or some unit, some activation unit at the output layer which is capable of giving me probabilistic distribution. So let's assume that from the output layer we are able to get a probability PR1 C of x for each class up to PRK C of x for each class, okay. Okay, so each of these is based on some sample phi s of the input features and a sample data ds, okay, ds n. Okay, so each of these models is based on a sample of the data set, possibly a sample of the feature set, and you are dealing with these probabilistic outputs. So for a new test point, what do? An average. You can, because now with neural networks you can associate probabilistic semantics if you use suitable activation units, right. So you can basically take simply 1 upon n average, right, and here on the board I used and this is alpha n, but this if you are taking a uniform weighted average, it just be 1 upon n. That was a very simple idea, but it turns out that if you have m data points and if the number of classifiers is of the order of square root of m, okay, that is not very small, large number of data set samples, but it is still square root of the order of square root of the number of examples. So 10,000 for example, you have 10,000 data points of the order of 100 classifiers. Under that you can show consistency results, and what is consistency here? We are saying that the error, the loss will converge to a notion of an optimal loss or base risk, the expectation of loss under the distribution of the parameters. Okay, so the loss will converge to the expected loss. So of course again this is just for your curiosity, I will be giving you reference for this if you want to read, but all I want to say is that even the simple idea has some interesting properties. And the other idea is that each single model viewed as an estimator of the ideal model has high variance, right, which is the variance is because you have shrunk the data, but if you could have less bias, if the assumption is of less bias, you do well. But unfortunately if it networks, deep networks like this, can you guarantee less bias? The network architecture itself is bringing in a lot of bias, right. So as I said, these models are more suited for, mainly motivated by decision trees, but yes, people have applied this to neural networks as well. So you need to make sure that the network architecture has reasonable flexibility, is not too biased, so that it serves a purpose. And if the bias is low, even with a large variance, since the models Ni and Ng are uncorrelated, if you do an averaging, you basically have the errors cancelling out. So this is the idea of, there is a noise cancellation that is happening in bagging. The errors are basically cancelling out, and yeah, this is also related to low correlation coefficient, rho ij. Okay, so this is the second idea, bagging. Now bagging happens somewhat in an asynchronous manner. You take these samples with replacement, which means that you can do them in parallel, right? The asynchronous. Have you come across asynchronous in any of your courses? Yes? Theory of computation? No. So I mean you can basically have these in parallel without need to talk to each other, these models. But what if you allow these models to talk to each other, even in the process of their building? That brings us to the third idea. Boosting. So what if we let the f1x determine f2x and f2x determines and so on fnx, which is these models are not asynchronously learned, there is some synchronization. The models are not learned asynchronously. That's the boosting idea. So what you do in boosting is, instead of kind of creating these samples independent of the weaknesses of a previous classifier, right? I built a spam classifier and I realized that this spam classifier is doing very bad for short text, right? For short emails that are spam, my spam classifier makes a mess. So why not do the following? Why not look at the classifiers the model examples where I am making errors and look for interesting patterns, interesting features there, so that I can improve upon my mistakes. Why should these be kind of learned independent of each other? Why can't f1 feed to f2 the mistakes it was making, boost up the importance of examples where it was making a mistake, and so on, and I will still consider a weighted average of all these classifiers, but after having talked to each other. Okay, so that's the idea. You upweight the importance of data cases that are misclassified by current classifiers in the ensemble. So let's say example xi is associated some weight xi I because it was misclassified. So xi I is basically increased. And based on this reweighing, I'll add a classifier that will focus on data cases that are crossing there. So prior to this, I was working on some classifier, say fi minus 1 x xi, and that fed into examples where I was making mistake, and based on this I'll add a new classifier that will focus on the data cases that are causing the error, and in the process I'll evolve a weight alpha. I'm using the same index I. Okay, so let's say j minus 1. Okay, so I'll learn and weight alpha j and a new classifier fj x. So that's the idea. Pictorially, all we are saying is I have my f1x, based on that I give weights xi to examples xi, based on which I learn a weight alpha 2 and an f2x. Now alpha 2 is being learnt along with the classifier. How much importance should I give to this classifier? Because if a very unimportant classifier makes mistakes, then the boosting weight associated with the examples will also be less, right? So if an unimportant classifier makes a mistake on an example xi, I would expect that the xi x associated with xi will not be that high. So therefore alpha I is going to be used to determine my, so this alpha 1 f1, then alpha xi xi, alpha 2 f2 x2, then again you will have weight xi xi reweighted, then you will have alpha 3 f3 x. This is the story, alpha n fn x. So you are learning a sequence of classifiers or models, it can be also regression, along with their weights, based on which you determine the weights to be associated with examples, and then this goes on. So again this can be shown to decrease error, assuming the base classifier can always achieve an error of less than 0.5 on any data sample, and then you can think of this as 1 upon k for k class. And again decision trees are very favorites here. I mean people often like to do this on decision trees because of the low bias they have. However, in lab 8 question 2 task 2 you associate boosting, not bad, boosting with perceptron as a weak learner. So this is like a little bit more intuitive in terms of weighted averaging, and what I am going to do is develop one model called the ADA boost. ADA boost is one boosting paradigm, one way by which you can determine your xi i's and alpha i's. ADA boost is adaptive boosting. Okay, and as I said, this is one paradigm for updating your xi update, for updating your xi I and updating your alpha j's. And we will just see that. So just to kind of show you this transition from bagging to boosting, again this whatever I depicted on the board I have on the slide. So what you are doing in the case of bagging is an ensemble of independently weakly learned models. When we say weakly learned models, we basically mean that the error is less than 1 by k, expected error is less than 1 by k. So bagging was just a ensemble of these independent models, and I have shown decision trees here. I mean we will discuss that, but it could be perceptrons. Okay, this is basically model 1, model 2 and so on. I am using for example trees, if these will be model will be trees, but I am referring to these as any models. So T1 to TB, these are the models. And boosting, what you are doing is you are propagating the error to determine your alphas. So the alpha in the case of boosting will come from the error of the previous model. So alpha j will be a function of the error from j minus 1. We will see one way you can come up with these alphas, and in the process what I have not shown on this slide is your weights for examples. So this model will also give weights to the examples. The xi will keep getting refined. So both of them are getting updated. Okay, and again think of these as general models, not necessarily trees. Now very interestingly, this is what happens in the case of ADA boost. Sorry, this is error j itself, error j. So the formula for the jth model or teeth model, let's. Use T here, the teeth model is basically 1 by 2 ln of 1 minus error of the teeth model divided by error of the teeth model. This is the form in AdaBoost. Again, what did we expect? If a model is very error prone, should it get high weight? Should it be weighted highly? No. So if a model is very error prone, let's say error is between 0 and 1. So if the error is close to 1, then what will happen here? It will become minus infinity, right? And if the error becomes close to 0, what would happen? The numerator will be 1, denominator will go to 0, and then the weight become very high. So I mean, it's consistent with what we expect. Something like this, right? So alpha t's, you will do a normalization at the end. Okay, so yeah, these are unnormalized alpha t's. You can do in the end, you can do an alpha t is alpha t divided by summation over alpha i's alpha j. Okay, you'll have to do this at the end. Question is, what will be an interesting form of xi update? This is alpha t update. This is one form. Now why this is useful, we'll talk about it possibly a little later. But let's take it from me that this is one form of alpha update. What would be an interesting update for xi? So his point is that if a classifier has very high error, you should not take its the weight resulting xi to be very, I mean, you should not take the contribution of that classifier to a misclassified point xi to have very high weightage xi. So that's one reason it should depend on error. But why should it then depend on alpha if it depends on error, and alpha is a function of error? Yeah, but one important point. So, but you struck an important point. Now, this xi, should it be only based on F2 or should it be based on all the classifiers so far? Should I be looking at the sequence or should I be just looking at a snapshot from the sequence from the previous time step?
All of them weighted by the alpha.
So you might want to look at all of them, the cumulative effect of everything so far, the error resulting from that, right? So let's see what AdaBoost does. Okay, so this part we already explained, error driven weighted linear combination. There's some motivation for this part. As I said, you'll need to normalize these later on, but something like this, alpha t is like y axis, error t is x axis. Okay, so this makes sense, and xi I expect to be a function of error t and alpha 1 to alpha t. Okay, so this is the form that is adapted in AdaBoost. So is it taking into account the cumulative effect from all the previous models or only the teeth model? Where is it cumulative?
That xi itself contains the exponential of alpha t minus.
Okay, we have made the update look seemingly simple, but it is actually catering to both needs. So again, I'll recap. What did we need? We need the alpha I capture effect of all models so far, right, alpha 1 to alpha t minus 1 and error at the tth step. That's what we wanted. Now if we set the alpha xi I to be xi I times the previous xi I times some form involving the current error, exp of alpha t delta, that is delta is basically measuring whether I made an error on that ith instance or not. Okay. So there are two parts to it. So there is this alpha t here. Alpha t is a function of the error, right? So alpha t already captures the error made by the tth classifier. So this effect is already captured here, right? So which means that the more weightage I'll give to alpha t, the less error the classifier. Is it correct? Sorry, I made this should have been ulta. Oh, sorry, this should have been on. This should have been chart, right? Nobody corrected me. If the error is small, right, the weightage given to the model should be large. That's what we wanted. This is the chart, right? And if the error becomes large, tending to 1, the alpha t should be very small. And this is what we wanted. Error should lie between? So you can think of this as 0 and 1. This is 0 and 1. This is half. Yeah, but this is how it should be looking like. Okay, so sorry. So this is alpha t. This is error t. Okay, so alpha t is going to be large when the error is small, and therefore for small error you are saying that I will take the xi I very seriously, resulting from the model's input into xi I very seriously. That is already taken care of here. Higher weightage model will contribute more to xi I. What about the other? We want the cumulative effect of alpha 1 to alpha t minus 1. What is helping me capture that? Yes? Is a pre-multiplication by alpha, by xi I. So this pre-multiplication by xi I captures this effect, cumulative effect of alpha 1 to alpha t minus 1. Yes? So you will have to kind of look at the lowest value. So as I said, some renormalization you will have to do. If you want probabilistic semantics here, right, if that's largely for this probabilistic semantics. Otherwise you can just go ahead. I mean, you can just consider it to be unnormalized weighted average. Nobody stops you from doing that. Ultimately you will pick up the class which is the most probable. So you are not going to necessarily consume this probability. You will use it only to find the most probable class. So it is not really important, but if you want probabilistic semantics, you may have to suitably normalize. Often the implementations just do this. So this is sufficient. I mean, for your perceptron case in the lab, this is sufficient. Okay, this is the AdaBoost algorithm. That's something you can implement. Initialize each instance weight, xi I to be just 1 upon m. All examples have same weightage. Learn the tth model by weighing example xi by xi I. Compute the corresponding error on the training set and compute the error driven weighted linear factor. That is what we are doing. Okay, so in terms of this sequence, you start with some xi I and then you learn the first model. Xi I is all basically the way you would learn typically, and then this does not require you to sample the data set, the entire data set. And then the step number 2 it says, well, now compute the error and also the error, compute the error, compute the alpha t and compute the new xi using these two expressions, and then move on to the next model. Okay, so you do it b times if you are taking b or m or whatever, based on whatever number of classifiers you are picking. So as I said, in the lab your TT will be perceptron. In the next class we will consider TT to be decision tree. Because decision trees are kind of favorites for both bagging and boosting. Okay, so in the tutorial 10 I have an interesting interpretation of ADA boost beyond just the intuition I give. So intuition was, as your error increases, alpha decreases, and as alpha is given more importance, it contributes more to xi. But is there some global error that the ADA boost algorithm is really tracking? Okay, if you consider CTX to be the boosted linear combination of classifiers until the tth iteration, and if you consider this slightly weird and strange looking error, okay, I mean this is really a justification post hoc. You develop some intuitive nice working classifier and then there is some justification. So if you consider this error, which is basically the delta error, now this delta error can be upper bounded by an exponentiated form. This is the substance of your tutorial 10, this upper bound. Okay, so this upper bound exp minus yi ct xi. What ADA boost does, right, is that it tries and minimizes this upper bound error. So if the claims made are, if the error, that is the sum of exponential loss on each data point, is an upper bound on the simple sum of training errors. The claim 2 is alpha t of the specific form actually minimizes this upper bound, and see this alpha t's are here, right. So this alpha t we are talking about. So this CT, which is some alpha t combination of the models, actually minimizes this upper bound over the delta errors, and the claim 3 is that if the classifier is slightly better than random, which is expected error is less than 1 by k, then ADA boost achieves zero training error very fast, exponentially fast. So this actually kind of tells you why ADA boost works and why these specific expressions.